Welcome back to the Cartographic Projection channel. My name's John. I'm a cartographer from Australia. If you haven't been here before, welcome for the first time. And if you've watched these before, welcome back. What we're going to be doing in this video is remeasuring the equinox, which we did in the very first video in September of 2021. It's coming up to the March equinox of 2022. Rather than recap equinoxes, if you want to know more about those, you can check out my very first video, which should be about here, that has a bit of rundown on it. What I will do is I'll go through the methodology again of the measurement. What we do is we have a stick and shadow, and using the angle created by the stick and the shadow, we can measure not only the sun's angle, but the angle that matches our latitude on Earth. So we measure the height of the stick, the length of the shadow, and we can work out that angle. And what we want to do is we want to work out an angle from the sun the same way. And so we need a point where the sun is directly above 90 degrees above the ground. And we know that happens over the equator at the equinox. So we just need to work out our length from the equator, and we have a corresponding triangle, which means we have the same angle, which will also be our latitude. So the equinox for March 21st, 2022 was actually at 2:32 in the morning. Not a lot of sun at that time of day. So we wait until solar noon, which was at 1:27 and 26 seconds PM. So doing our measurements, there's my board, which I've actually leveled up this time. And measuring the height of the stick and marking out the shadow at solar noon. This is all the part where push comes to shove. And you can see I thought it was 127 and 21 seconds. I was 5 seconds out. Don't know why I did that. So we have a height of the pole of 488.5 millimeters, a length of the shadow of 371.5 millimeters, and working out our figures, from our geometry we get an angle and our latitude of 37 degrees, 15 minutes, 9.62 seconds. So how does that fare with where we actually are, the accepted value of where we actually are on the planet? Well, we've got what I worked out from the shadow length compared to our actual spot on the globe, giving us an error of 9 minutes, 6.41 seconds, or an actual percentage error of 90 degrees of 0.041 seconds, less than 0.1%. And you can probably tell that I'm pretty damn happy about that. Also going for the circumference of the Earth, just like Eratosthenes did, we've got our accepted figure there of 40,006.9 kilometers. Going through our mathematics for our position, I get a calculated circumference from my measurements of 40,046.5 kilometers. An error over 40,000 kilometers of 39.6 or 0.099. Once again, less than 0.1%. So as you can tell, I'm damn happy with that. Did I make some errors? Yes, I probably did. So probably fractionally out on the height, probably fractionally out on where the top of the fuzzy shadow was, and that's a point of argument for anyone. But obviously, in my case, these errors managed to compensate for each other, and I've come up with a damn fine figure. Leveling the board, unlike what I did back in September, actually made a hell of a difference too, obviously. Once again, I'll point out that the error for both was less than 0.1%. I might keep hammering that home to people all the time. So thanks for watching. Hopefully you enjoyed this. If you did, feel free to press like and subscribe if you haven't already. That would be great. I'd be very grateful. Until the next video, I hope you enjoyed this one. Please take care and bye for now.